I teach Rust and Rust related things for Rectoff and also for rare skills. Um, the I guess if part of my introduction could be my motivation. My my goal with Rectoff is to help Web3 developers who I think in the Solana ecosystem and in other ecosystems often are not coming from a background like myself, where you studied compilers, you studied programming language theory, and that's what you lean on when you're writing and reading programs in the space. Instead, these often I think people are coming from a variety of backgrounds, which is wonderful. But my goal is to try and then help those people understand what's going on at the lower level, what's going on with memory, to help make these things which are perhaps mysterious less mysterious, because it's not that people can't understand them, it's just that they need someone to help show them what is going on. So that's my goal, generally speaking, and that is what prompts me today to talk about the Solana virtual machine, memory and execution. I have tried to trim the lesson that I gave on this, that Mike, you were speaking of then, because I actually ran for 3 hours in that lesson. So this is going to be a a reduced version, and also that lesson is built upon a bunch of context that I set up, where I talk about memory in theory, prior to talking about its application to the Solana virtual machine. But we'll do a bit of a crash course, and I'll make sure that I'll try to catch myself if I'm going to talk for too long. And also, I prepared these slides to try and force myself to have a trimmed down version. But if we get to the point that we need to look at the Rectoff material, I can always switch over to that side of things. But if anyone is interested by the things that I communicated there, trying to get a low-level security-minded understanding of what's going on when interacting with the Solana ecosystem, I very much encourage you to apply for Rectoff and join Rectoff. I think you'd like the course. So for today's lesson in particular, I want to talk about a Solana validator first, and I want to talk about it from the perspective of what memory it is using in order to achieve the functionality that we want. We're thinking about a validator as being a node in a distributed ledger, like a blockchain. And then I want to talk about, if we're going to have Rust programs as user-defined code, smart contracts, well, how would we want to compile them and deploy them into these validators as nodes on the network? And what are some things that we need to consider when we want to achieve such a thing? And that will inform what design we're going to, or I shouldn't say we are going to, I should say has been undertaken in order to achieve this. And then we will look actually at snapshots of code, looking at executing those programs. So once we have in some way stored these user-defined programs, we want to be able to execute them from chain, and we want to be able to, importantly, do it safely. And I'll talk about the particulars of what that means exactly. So what I'll get into first is a bit of a primer to do with memory. So when we think, oh, and by the way, I'm very open to there being questions. So if something I'm saying doesn't make sense, feel free to ask a question. And also, if Mike, maybe you'll have to help me with some translation if I can't read the characters.
Yeah, sure.
And that question, James, I wish I could speak Chinese. I wish I could speak anything other than English, but unfortunately, I think I can say ni hao, and I hope that is yeah, I hope I even pronounced it close to right, but unfortunately I only know English. But my my memory primer here that I want to talk about is, so when we are starting any process on an operating system, make that a in our particular case, I want to think about a validator as a process that is coming from Rust, like the Agave validator. Our operating system has in some way to section off a chunk of memory for us. And so if we think of an abstract representation of what's going on, this isn't exactly how things are laid out on our RAM in our actual computer, but this is kind of a as I said, an abstraction that the operating system is going to provide us that we work with, and it will worry about the details behind the scenes. And so we have some address space that we think of as these hexadecimal, literally memory addresses, and there would be some of them would be higher and some of them would be lower. And laid out inside this address space that we have been provided, we want to have access to the instructions from the compiled binary. Those instructions are the actual things that we would execute. Sure, no problem, Julian. I will provide the slides. Those instructions are what the actual program that we want to execute. So when we write our functions in Rust, whatever we want them to do, this is the instructions that will actually be executed. And there might be some other information, like we want to store all of the possible error messages as strings, everything that comes from Rust like that, that's extra information. And we think of all of that as being in what we call static memory. And sometimes it's read only, like we don't want to be able to change our instructions after our program is loaded into memory. But then once we have our instructions need to process data. Over the as the program is running, we need to have some data processing is deterministic, as in we know the size of it, we know how it's going to be laid out in a very predictable fashion, I guess I should say. And we would use stack frames. The call stack is where we think of that data being processed. But then we also sometimes want to talk about heap memory. Heap memory might be used for data that we know is dynamic in size and it's growing. And there are trade-offs to where we're storing information in our program. But I just want to make the separation that we have static data, that is the information that we are taking from our binary and bringing into memory as we want to run our program. And then the stack and the heap are going to be populated as we process those instructions and go through the program. Okay, so that's a bit of a primer there. So now I promise that it's not all going to be just crazy amounts of text. I have visualizers and pictures to help, but let's start off by talking about a Solana validator, and we'll think about it as a Rust process. So I use Agave as all of the links for everything that I use. I'm familiar enough, at least, with that validator. But a validator could be written in realistically a different language than Rust, but I'm going to look at it from the perspective of Rust because that's what I'm familiar with. So a validator is essentially going to be a long-running Rust process. So something like this is going to need to implement all of the relevant blockchain logic. All of those instructions need to have the logic to do things like transaction processing, management of the state of the accounts, the ability to do consensus, interact with other nodes that are running other Rust processes over a network. All of that needs to be able to be accounted for in this Rust program and thus this Rust process. So we can think that there are relevant data structures as well, and we might not often think about them from a smart contract perspective more than we just grab an account, and we grab an account from this, this some blockchain we don't really know, maybe, or well, often people do if they look at the details, but I think a lot of the time people don't really think about where is this data stored. And the answer is that this data is stored inside the memory of a validator in the network, and thus is propagated via some agreement protocol to all validators in the network. So let's have a look at some things that I'm talking about. So when I'm referencing data structures that I say are in the ecosystem, something that stores all of the accounts is an accounts DB. And so this is the data structure that is inside the Agave validator, inside the accounts DB crate. And we can go to that validator and we can look at the actual source code for this and look at the methods and how does this provide the access to these accounts to the transactions that come into the validator to be able to process on. So this is just a struct, and a struct will just be inside memory of one of these machines somewhere. Much the same way, we can think of a bank as I guess, as the block under construction or the block under process. And this is just a struct in memory that we can go and we can understand. And so if I am to show what I mean in terms of like how I want us to be able to think about this stuff. So I have a visualizer here that I made, and this is Rectoff themed. So Rectoff themed is like matrix themed. So I hope you guys like green, fluoro green at least. But what I'm trying to show here is this idea. Whoops, this is the wrong one. I want to show this one. So I want to show how we can link that idea that I was showing there of actual source code and think about it as ideas. Like, what is the idea of what's being implemented as we do this? So a validator, say Solana validator.rs, it starts off as some Rust function. So here it's going to have a main function main, and then all of the validator code. And of course, there's going to be tons of code. Like, this is a massive program. But at the end of the day, that is all it is a Rust program that is then going to get compiled down, say, into a executable. That's why I have .exe here. And that is just going to be a binary format that our local machine that we're running the validator on understands. And so say this was run on my machine, it would be an x86 program. So we get some binary, and that means that it's when we want to instantiate that and to running the validator process, we ask our operating system to provide us with a section of memory. And these instructions here, they get provided into that data code segment that I spoke of before. If I'm just pictorially like fanned out, whatever is going on with this process over the lifetime, it needs to handle all of the things that we think of this blockchain being able to do. It needs to have the ability to propagate propagate blocks and do voting. It needs to be able to ingest transactions, make sure that they're valid by verifying signatures, lock accounts, load from those locked accounts. We want the ability to execute smart contracts, load in programs, whatever. When the transactions are valid and we have modified the state of those accounts, we want to be able to commit those and have the modified state agreed on by all other nodes in the network. Of course, we want compute metering so that compute costs money in these systems, and things like logging, return handling, all this. So this is the idea of what this program needs to do. And we often think of this as being connected to some series of blocks in a blockchain. And so we sometimes are reading from the blockchain. We're reading the previous blocks we might think of. And sometimes we're writing to the blockchain, appending another block. But I want to point out that this up here, it looks like this is something separate from this diagram here, but there isn't a separate thing like this. This is the data that is inside our running process. And I think it is important to remember that in our mental model, that there isn't some other world where these blocks live. They live in the memory of the validators in the network. And so that's what I want to bring up as just an idea, something to think about. And that means that when we have this program that I show here, this validator code needs to be able to instantiate the ideas that we need here, which will mean it will need some properties. There are going to be some properties that we need when we write this program that we think of. They should be invariant. We don't want them to change. We want them to always be true, no matter who's running it, under what conditions. So things like determinism. We want to know that if we are taking a sequence of transactions, when we process them, that they will yield a deterministic state. And this is regardless of externalities, like if we're running on this OS, or if we're, it's this slow, or what's getting processed, or are we running other things at the same time? There's other programs that the scheduler on our computer is interleaving process instructions. Regardless of that, we want it to be deterministic. And I also mentioned, which is going to be thematic for this, we want there to be this idea of isolation. And why I say this is because if the validator is storing things like all of the accounts in this account DB and the block under construction by the bank, then we want to, if we're going to have user code able to be executed in such an environment, we want to know that it is soundly separated from this information, in the sense that it only reads in what it requires to do the processing, and it only writes to what's required. So that idea of a property of isolation is important to think of with this validator. Okay, so now that we have that idea, do we have any questions on that? Actually, I might not run first. This would be a good opportunity to ask, because I'm going to talk about the actual process of compiling down one of these smart contracts, and how does that exist on the network next. Cool. So given that go ahead,
don't worry,
Mike.
Daniel. I just try to translate, but it's not related. It's not it's okay. Thank you. Continue, please. Go ahead.
Okay, cool. No problem. So so with that idea of something that we would like to do is being able to run user code, and being able to run it separated from the rest of the program memory. That's what I am thinking about here when I'm talking about smart contract compilation and deployment. If we think about it, a validator is a environment that has a lot of critical code and a lot of critical data. And I mean, and this is critical, like it's guarding a lot of money that belongs to a lot of people. There are a lot of people that have a stake in the success of this program and this distributed network of programs running successfully and safely. And we don't want the ability, or if we're going to allow the ability to have user code in the form of a smart contract that other people are writing, they're submitting, and then these validators are running that code, we want to know that isolation is preserved in a way that even if that were the most malicious user who wanted to screw with the network as hard as they could and make everything bad in any way that they could possibly think of, whether that would be stealing funds, denial of service, things like this, we want to know that that is that the attack surface is reduced as much as possible. So that's why I bring up here this problem. Smart contracts are user code running via a Rust process with critical data, and I say e.g. all Solana accounts, and the problem is we don't trust users. So how are we going to run user code inside the memory, as I show, like this? How are we going of the process? How are we going to safely be able to section that off? Luckily, this is not the first time a problem like this has been encountered. And so maybe I'll take this moment to do an asterisk. The stuff that I'm communicating in this lesson is not informed by being in contact with the people who made the design choices and the decisions for what to do with Solana. It's just coming from knowledge of operating systems, seeing what I can see has happened, and doing a bit of inference for the decision. So just note that there could be a Solana developer or someone who said, well, actually, the reason why we did this is different. So this is just my interpretation of history, I guess, and engineering. So why I say it's lucky that this has been solved before is this problem is not so different from what we have in operating systems, where we have on our computer a kernel, the operating system kernel, running. Sometimes we want to do this. We want to run user-written routines inside kernel space. So candidates for when we might want to do this is if people want to write performance diagnostics, people want to be able to check things on their NIC, their network card. They want to be able to write their own programs, insert them into kernel space to get information. But kernel developers say, we're scared to run user written code in kernel space because the entire operating system is there. How are we going to section them off from being able to screw with the stuff that we don't want them to do? And the answer is we need to have a virtual machine inside that space. And so this is where we enter with eBPF. eBPF is a reduced instruction set designed to run user code in a virtual machine in kernel space. So cool. We get a VM, we get a small language that's like a register based like assembly language, and we say this VM can run this language, and the kernel in this case provisions that memory and allows it only access to its box, where this is what you can work with. And users, feel free to write the logic, because we as kernel developers, we know that you only have a window into that box. That's your view, that's your world. And so this lesson is what I think happened is people thought, well, perhaps Solana could use eBPF, and thus it gets the same idea. We can have user-written code running inside a sandbox on inside a process that has critical data otherwise in the system. But there are some things that I guess were desired to be changed. And so I just give one example of that. Heap memory. So original SBPF run or original eBPF run raw, it didn't have heap. I'm not sure what it's like today. That might be a thing that you could perhaps add in. I know that eBPF has grown a lot over the years, but at least at that time, that wasn't something available. And so if you think about putting in those changes that Solana wants, that's where you have SBPF. And so this is modified eBPF with the changes that Solana desires. And so to encapsulate again, what is the idea of that? This is a virtual machine run inside a Solana validator that is going to execute user code, the smart contracts, in isolation. And those user code are going to be written in the SBPF instruction format. That virtual machine will be the SBPF virtual machine. I feel like I skipped the visualizer. So I'm going to go back because I want to give some intuition about what the problem is that we're trying to engage with in such a scenario here. So let me go back. So the idea, sorry for doing it a bit out of order, but the idea that we left off last time when we were looking at this visualizer is if we have created a validator that is a running Rust process, what exactly do we mean when we say we want to provide user code that can be executed here? So I'm just going to talk about the deployment side of things. I might span out a little bit. I hope this is still readable. Let me know if you need any changes. But the first step is, well, the thing that we want to provide a transaction to needs to be running. So this process, this validator is running somewhere out in the wild, and we have the ability to send a transaction to it over a network. But before we create that transaction, we need to have a contract.rs. So our main function, sorry, not our main function, our contract code is going to be the logic and everything that our smart contract is. So we write a smart contract in Rust, say, and then we compile that down. Now, we compile that down to the SBPF bytecode format. I haven't explained exactly how we compile that down yet, but take it for granted that once we've decided we're going to use SBPF, a modified version of eBPF, and that's going to be our instruction format because it's got all these nice things that we like, and there's a lot of benefits to it. Say that we figured out how we're going to get from Rust down to there. That would then mean that if we can do that, we can create like a contract.so, an ELF file that is the binary that is in the SBPF bytecode format, which we have decided is our instruction set for these user-derived programs. So then we could go to, say, the Solana CLI, and we could say, I'm going to create a transaction that is a series, the message of such a transaction is a series of instructions. I want to create an account on this system, on this blockchain. I want to create an account. And remember, that's actually just some information here in memory. But I want to create an account in there. I then want to, using the BPF loader, I want to write the contents of my contract that I compiled. And then I wrote finalize here, say, you might want to make it immutable, say. And then you say, okay, this is the logic that I want to be saved in memory on chain and thus accessible to anyone on the network to invoke via a transaction. So we send a transaction to our validator that must receive and verify it. So make sure that the signatures make sense. It's a well-formed transaction. And then once we go, okay, it's past our standards that we believe this is a sound transaction that we're fine to engage with. Something that we wanted to do was create an account. So we're going to need to be able to fetch, like, lock account states that are required. And then once we have access to those account states, so remember, that's fetching and locking information that's in accounts DB in memory here. So we've got our lock on those accounts. We then decide we're going to process those transactions. I actually go through and put in that account the actual bytecode ELF file. And once we've done that, we can unlock the accounts, and this gets essentially recorded in the ledger. It's seen and thus propagated so that other validators in the node and thus RPCs can read off and be like, cool, this smart contract exists in the network now. We can see it. So that's how we might store a user-derived program. And I already spoke about the existence of this SBPF bytecode being and why that was something that we might want to use. I'll show here if we want to gain some intuition for what SBPF looks like, we can go to the ANSA GitHub that has the SBPF, how should I say, the SBPF repo. I'm looking for the word repo, which is a fork of this says a fork of RBPF, but there we go. RBPF was a fork of someone else. So this is a Rust implementation of eBPF, and this fork here is going to make the changes that Solana wants. I see that Julian has asked, except for heap, are there other differences between eBPF and SBPF? I would say that there are going to be differences in terms of all regions of memory. There is a unique memory model to Solana that is provided that I will talk about shortly. But you can think of things like the call stack and stack frames, the limitations and addressing of these will be unique to what Solana wants to work with. There may even be differences between validation. I think that there are limitations to what you are allowed to use in order to keep consistent with a blockchain system. These might not be limitations that exist in eBPF, but you should think things like we don't necessarily want access to, well, definitely we don't want access to anything that provides non-determinism, right? So there's no threading, there's no concurrency, there's no access to random, there's no, and then things like if you want to work with floating point numbers, if I'm to understand correctly, floating point numbers are something that can often be like architecture OS dependent. And so SBPF, if you want to do floating point numbers, it has its own routines actually in SBPF to ensure consistency for how floating point operations are done. And so that's an expensive thing to have. Is instead of that done natively on your machine, that's done through a series of SBPF instructions. So I'm sure there's more to the picture than what I described there, but you should think that what's changed is anything that is relevant specifically to the Solana environment that they want to be able to fix for their use case, which is doing smart contract execution. So in this repository here, I got it that time, we can go to the documentation. And here we will get a little bit of a flavor for what the bytecode is through its instruction set architecture. And I just show this to give you an idea that you can go and investigate this yourself. We're not going to try and drill down too hard into the details right here. But we can think of is it's a register-based system. So it has this R0, R1, R2, all the way down to R10, which is not a general purpose register. And then we have a program counter. So these are registers that we can store data in. And if we go down to the instructions, we'll see that we have with the instructions, the opcode will be provided. We'll have a source register and a destination register, perhaps some offset or an immediate value. So this table illustrates or maps out what are the instructions afforded to us in this small little assembly language. So adding, subtracting, multiplying, all of our arithmetic operations. We need the ability to load and store from memory locations, control flow operations, being able to jump to different sections of the bytecode, which is in turn different sections of our actual compiled program. Things like this. We need all of this stuff needs to get supported. And so this gives us an understanding of, okay, what are the instructions in this SBPF language? But this repository does more than just defines what the instructions are in documentation like this. It also provides the implementation of the VM and how the VM executes those instructions. So if we go into the source repository here, we'll see that there is an eBPF RS, and this should, if I go, oops, I've gone to the wrong one. That shows what I get for VM. Sorry, that's what I wanted. That shows what I get for trying to do everything from memory. But if we have a look inside this SVPF file, it will have a definition for, wait for it, it's going to happen. Well, that looks like it. A virtual machine to run eBPF programs. Now, remember, it's to run eBPF programs, but this is a fork. So the eBPF in this case is modified it to SBPF as we commonly know it. And this is a struct that has a bunch of fields which are related to the information that we just had a look at. So the list of registers that we saw before, it's going to need those registers. It's going to need to have memory. We spoke that there was stack, and I mentioned the difference in heap. So when it says memory, these are the memory that it's talking about. And there is going to be, I don't believe we'll see it here other than when we need to load, execute a program. So this VM is able to execute a program which is provided to it via an executable. That executable is an ELF file with an SBPF bytecode payload as what it has. So let's have a quick look. And I'm not expecting to show you this and you guys then feel like you've understood completely this code base. I'm just showing you this is something that you are able to navigate and go and get some understanding from. If I show you where it is, like I said, it's in the ANSA GitHub. You can go and it is the kind of thing that it takes a little bit of time, but it's achievable. You can go and you can understand how this works and get an understanding of what is happening with your programs that are executing on architecture. So if we go down, we should see our ELF loader / relocator. So this here, this is our representation of a the SBPF program. And so even just right here where my cursor is, it says SBPF version, like the version of it. We see things like the read-only data section and the text section. So that's important to understand because the read-only data section, that's where I was talking about there being the existence of things like the error strings and anything that we provide along with our program that it needs. But we also have the text segment, so the actual SBPF instructions. So these need to be accessible in our by our VM. It needs to be able to read in an ELF file, elf.rs, right? Read that in and have the registers and the memory layout to be able to execute those instructions, process them. Okay, so with a bit of an exploration through there complete, now that we know, we've agreed, cool, that's what we want to use. We want to use SBPF. So what's the next step? How do we do it? Because remember, there are changes. There are changes. So you can't just use eBPF. You want to modify it to some degree, right? And so you need to be able to go from a source language down into SBPF. And so that's what I'm going to talk about here and as part of the compilation. So diagram 1. Let's see if I got this right. Diagram 1. Here we are. So what I'm showing here is a diagram that is representing the phases of the Rust compiler. So we should remember that when we write any Rust program, or any program for that matter, it has to in some way end up being able to be processed on a CPU. The CPU needs it in some instruction format that has the ability to process. So there are two options. I guess, well, I mean, maybe there's a third, but at least I'm going to talk about two options. You can either have an interpreter, so you compile those instructions down to an interpreter that does this, or you can compile your instructions down to a native binary format. So an interpreter would be something that works on the SBPF directly, and a native binary format will be something like x86. And so we will need we talk about the compiler compiling down to that format. Now, that being said, don't think that we ever can't, that I just heard myself back. That might have made it sound like only in one situation do we need this compiler. We still need the compiler. We always need to compile from our source language, Rust, that we write our smart contracts in, down into the lower representation. So without thinking about SBPF now, just thinking about what is the Rust compiler, it is a program. It's also written in Rust, but it's a program that ingests main.rs files, say whatever our source files are. It takes them as input in, and then its goal is to provide us with a binary that is also valid. And so what does it mean for it to be valid? We need to know that it's well formed and that it upholds all of the variants that the language that we're compiling down promises are upheld. So things like in Rust, we think about programs being strictly typed. So you need to make sure that all the types make sense. And so as we take the program in, we want to essentially change it into being what we call an abstract syntax tree representation. And once we've got that in there, our first goal is to go, okay, we've got our AST. Now let's change the format of this into something that we can do analysis of to make sure that we uphold those invariants that I spoke about, like the traits make sense, the types make sense. And we'll see with Rust that we're not doing any invalid memory things, like that the memory it's memory safe programs, what I'm trying to say. So we change down into a higher intermediate representation, and we do rounds of analysis on our program here, like making sure the types make sense, making sure that the traits make sense, that we have type coherence, this sort of thing. And then we make sure what we go down next into our typed high immediate representation. We'll make sure that if we're trying to call unsafe functions, that they're inside unsafe blocks, like rounds of analysis like this. And then finally, we get down into the mere intermediate representation. And here we do the borrow checking. We make sure that we're not violating memory safety in our program. And monomorphization is we change all of the generics into being the actual types that do actually end up getting called with the program. So these are sectioned off into a different box. These are the Rust intermediate representations. And then what we can think of is all Rust programs agree that they have to go through this pipeline. But after that, when we get to code generation, things start to split. This is where we get a fan out, because we don't have to use LLVM as our code generation. We often do. You can replace in a different code gen backend if that's what you want to do. But say that we are using LLVM, that needs to know all the different targets that it can go to and be able to change whatever formats are coming from up into the compiler into the actual assembly targets. And so here, this version of the compiler, the normal Rust version, it doesn't know about SBPF yet. So that needs to be added so that this pipeline can be used to create SBPF programs. So what I then talk about is, okay, so we want to be able to add the SBPF target. We want the Rust compiler to know about it. So Rust already supports compilations to things like eBPF, but to get to SBPF, it's going to need to be forked, and the target is going to need to be added. So much like when I showed the SBPF fork, inside the ANSA repository, there is also a Rust fork. So this is the Rust compiler. It says a fork of the Rust compiler that supports the BPF targets. In particular, this is going to support the SBPF targets. That's what we're interested in. And so the juicy code that makes up the core compiler of the Rust compiler is inside this compiler directory. And there are many, many crates supporting the Rust C world. But now, if you remember on the diagram, at the target is changed down here. So really, we don't want to change anything that exists inside this box to support the target. We just want this box and the Rust compiler to know that that target exists and be able to make sure that it invokes the right version and things like this. LLVM is going to need to be the thing that actually generates the bytecode, but let's have a look. So all of these crates, for the most part, and there's a lot of them, we don't need to have, or the Solana developers didn't need to touch them. What they could do is go into this Rust-C target, and this one needs to have some modification. And I'm going to go to my so if we have a look up here, I went through to that Rust-C target. I just cheated to make sure that I went to the right file instead of trying to do it by memory. But inside source spec for specification, there's this mod rs. And so this contained all of the specifications for the targets that are supported by, where are we getting? I want to get into the juicy part. Here we go. All of the targets, supported targets. There you go. Supported target. There we go. Supported targets. So all of the targets that are supported by this compiler and added into here. All right. Added into here in this fork are these Solana targets. So we have SBPF, SBF, SBPF, and then SBPF V01234. So these end up being aliases of the same thing. You can think there's V1, V0, 1, 2, 3, and 4 are added to the compiler here. And there's a few other places inside here where you can see reference, like it's always inside this Rust-C target here, but there's a few different places where you can see the reference to SBPF. I think maybe even inside, yeah, I'm not going to be able to do this stuff by memory, and I'm very cognizant of time. But there's other places where this is referenced, but that's not where we're doing the juicy part of actually figuring out how to turn that into the bytecode. As I mentioned here, it's the code generation part that is going to turn it into that declared target. So, once again. So to get SBPF code generation, if we are indeed just going to use LLVM, which is a pretty standard target or a pretty standard code generation to use for Rust, you're going to need to add support for using SBPF for LLVM. So same sort of deal, fork LLVM and add the SBPF target. So once again, we look here and we see that Anza has created another fork of the LLVM project. And why has it done this? It's done it to support SBPF, right? Like that's what it wants to support. And so using I'm not going to try and navigate this once again. I already found it and I'm just going to use that link. But if we go through from LLVM project, LLVM lib target, SBPF, there is an entire module of C++ code, which is doing lowering from LLVMIR down into SBPF. So all of the code exists here that that is giving us our binary format. So we've got two forks and we connect them together to go down. And once we've done that, the diagram on the left here changes more to the diagram on the right here. So this is originally Rust source code, but this is Rust source code intended for a Solana smart contract. And there isn't really a modification up at this section. Instead, it just says it needs to be aware, which is why we looked in Rust-C_target. It needs to be aware, and we need to be running a fork of Rust-C that contains that modified Rust-C target to know about SBPF compilation. And then once we get all the way down to the code generation section, we use our custom, Solana fork of LLVM, Solana LLVM, and we've added this SBPF target here. So that's how we modify Rust to be able to get access to the SBPF bytecode. And all of this is happening behind the scenes because we don't really think about it. We just use cargo build SBPF, right? We don't think what's happening behind it generally, unless you're interested, and then you go and you look at these repos. But it's just packaged up in a way so that it just connects to all the right things to give you the SBPF target. What are some good resources to learn about LLVM? I think if you type in like LLVM wiki, and I think that, at the end of the day, the way that I always learn about this stuff is I just go and read the source code and I just try to go through it. Now, I will say with that, LLVM is not something that I know much about, mostly because I'm not really great at C++. If I ever try to write a C++ program, I'm almost certainly going to do something, add some behavior in there that I don't want, and perhaps not even do the thing that I do want to do. So I can't say that I'm an LLVM guy, but at least that's the component that's there. And my way of learning about the Rust compiler was to read the Rust compiler source code. So I imagine that approach, is probably the best way to understand what's going on in that code base. But it is you have to think that anytime you're undertaking learning about these massively complex things, have in your mind, this is a large undertaking. They are complicated systems, large systems, and it doesn't happen overnight. But if you go in with the mindset that you are just going to quickly go and learn it and understand it fast, you will be disappointed. But if you just go with the idea of, okay, well, maybe, I'm just going to try and figure out how this component works today. And you just take the little wins along the way of the parts that you gain. And eventually you just chip away at it and you get more and more knowledge. But if your goal is like, I'm going to learn LLVM and I'm going to do something with it in 2 weeks. Yeah, might be hard. Not impossible. It depends what your background is, right? You might be fine. Cool. So this is what I talked about. Is this gets packaged up into cargo build SBPF, but ultimately we've changed just a couple of components in the Rust compiler pipeline, and now we can get our target. So let's say that we do that. I should go to. I want to go to here, but let's get rid of a few of these things because I'm going to get confused otherwise. So if that's our first one and that's our second one, or is it the other way around? Yeah, there we go. So that's where I've just explained. Remember when I first showed this diagram, I explained we're just going to take for granted the existence of something that does this step of going from Rust to object file. So what I just showed is you have to do those forks, and there's actually a ton of engineering effort that goes into simply doing that step. And then I showed that what is this SBPF bytecode? Like, what even is that? And that was that other fork that I showed you, where we had the instruction format, the ISA there, and then I showed that there's defined this VM, and we define an executable, and the VM's going to ingest the executable, and it's hopefully going to process this bytecode. But at the moment, we've just talked about storing this program in an account. That's what we've spoken about. So next, the next thing that I want to talk about, how do I go? Yep, there we go. Cool, now I got my pointer back. So now I want to move over to talking about smart contract execution. And once again, I should start with my visualizer. I wrote them for a reason, right? So here, let's say that we've stepped off from this point where we've stored our user-defined smart contract in an account in blockchain memory. Now, we want to be able to submit a transaction to invoke that program, execute its logic, and update the state appropriately. We've chosen SBPF because it has a VM with isolation that we can use for our use case and make sure that it adheres to all the requirements and invariants that a blockchain system needs. So then what's our first step? If we've stored the program, we want to execute it. Well, we need to have the contract address, right? So the contract address, it has like some, an address, some hexadecimal address. So we can think that we're essentially saying, okay, I know what the Rust source code of it looked like. It had this function and this, you know what I mean? And so what you can do is you can provide it I say function index here. I guess I should have said instruction. That would have made more sense. But you provide it, you say from this account, I want to call this function, call it myfunc. I know that myfunc has discriminator 2, right? So I provide it with a 2. And then you give it a list of accounts. I want write access to this account. I want read access to this account, yada, yada. And then you bundle your transaction up and you send it over the network to get received by the validator. Same thing happens. It receives it and it needs to verify that this is a well-formed transaction. And then it does the same thing. All of the permissions on the accounts that you have here, it fetches and locks those accounts. If it only needs read access, it makes sure that there isn't already a transaction using write access for it, in which case it wouldn't be able to read from it. It would need to wait to get that lock. But if that isn't the case, then it gets a read lock to it. And if it wants write access to one of these accounts, it needs to make sure that no one is accessing that account at all. And then it gets a write lock to it. And if anyone else was reading from it or anyone else was writing for it, you would need to wait to get access to lock that account state until that update, the transaction is finished. So you fetch and lock the relevant accounts. So you're going to have read access to the account that has the ELF file that we've provided, the smart contract. And we can think that we are probably the instruction. I mean, the instruction is going to be BPF loader execute this smart contract, right? Like that's what we want to do. And so once we've decided that we want to do that, this is where what I showed with that eBPF VM, that has to spin up the virtual machine to provide the isolation window so that whatever's processing here, so we've retrieved from blockchain state. Remember, this is actually just stored somewhere here in memory, but we've retrieved from blockchain state this smart contract SO, which is just some binary that's the SBPF bytecode that we stored before. So I'll show where all this stuff is, but what we do then is we create another layer of virtual memory. So we can think low address, high address, and we store in the bytecode or text segment that binary, which this is in that eBPF VM. Remember I showed that like you get your executable and your executable's got its text segment, it's got blah, blah, blah. You want to read from that executable and store into your static memory, which I remember I talked about these sections being static memory. It's kind of the same thing over here, but all of the addresses and all of the layout is different. But we want to load into static memory that bytecode segment, any information we need, like the read-only data, error strings, maybe things like that. And then there's going to be input to the program, like instruction data, like if you're going to do a transfer between accounts, you're going to token accounts, you're going to need to provide an amount. And so that's input data that gets serialized in. And then you reserve some space at these addresses, for the stack and the heap. So we want to process these bytecode instructions, and we're going to need to, add data to the stack, add data to the heap, depending on what's going on. But we should always remember that this looks like a totally different thing than what's going on here. But this is running on this system, right? So this memory here is mapping back in some way to what's on this validator here but we've just appropriately sectioned things off so that we feel confident that we've sandboxed it and we're preserving our isolation property. Cool. So I'm going to go into the details of what's going on here, but what I'll say is, assuming that we can process all of these instructions and go through, and we don't have any error that occurs in our program, then we record that we unlock all of the counts, update the relevant accounts with the data, of course, that the newly changed data, all of those ones that had writable permissions, and we record the state in the ledger. So that's like the mental model of what's going on. Doesn't the stack grow down and the heap grow up? That is what we think of as happening on a like a traditional operating system. However, for eBPF, well, SBPF, this is defined by, in that repo, that we get to the Solana developers get to define the behavior of how this stuff works. And actually, the way that the stack grows, well, not necessarily the way, but more than just direction. Think of whether you have fully spaced out stack frames, or whether they only hold enough. Like you might have, what am I saying? Statically sized or dynamically sized stack frames, this sort of thing. The manner of how this stuff works it does change over the version. So SBPF 0, SBPF 1, how all this stuff works, it changes. So what you said there is, doesn't the stack grow down and the heap grow up? So first of all, what I want to say is, we think sometimes as the heap growing up because we do know that the stack grows down. Really what we should think is the heap is allocated under the stack. It doesn't necessarily grow up, like the stack grows down like this. The heap grows, or it kind of just gets filtered out for however it needs to happen. And what I mean by that is, when you decide that you're going to store something on the heap, it will need some allocator that is going to talk to the operating system, or in this case, it's going to talk to this here. The allocator will talk to this program here and decide, how am I going to allocate that memory? This here will need to talk to the operating system to go, can you give me a spot where I'm allowed to allocate memory? But it doesn't necessarily grow up. It just fills in as appropriate, dictated by the address that the allocator gave back to it. Now, those rules are what we think of as existing for a Rust process. However, the rules that happen here are just whatever rules exist. If I know I got it here. Whatever rules exist inside source. It's always source. Why would I? Whatever exists inside, say, more, it's not memory. Yeah, memory region. So here there's like this idea of gapped memory, which isn't true anymore, but there's memory regions here that are defined. I'm going to talk more about this later, assuming there's time. There's this thing to do memory management, although I don't think this is not so much what I wanted to point out. Where are we going to see the stack? It might not be so easy to see unless I go into eBPF here, but what we can think of is we store things like the virtual address of the stack region, and we want to know, I wonder if I go here, call underscore frame, no, frame pointer. I'm not going to be able to do it well from memory, but those rules are defined in here. Was there a VM process pool to execute transactions in parallel? Well, what you can think of is inside this transaction. So this transaction got sent to execute the logic inside this program that was stored in the in the blockchain. Within this process here, so this memory, this virtual memory is here for this process. Inside this process, there is no parallel execution. However, if as the validator is processing this instruction, should another transaction come in, want to access even the same account, because you only have read-only access to these programs. You never write to them, right? So you could, but say that it's another one, even say it's a different account. As long as the accounts that are declared here, there is no conflict between the read or write locks that need to get acquired in this stage, they are essentially completely independent of each other. And so they, at the same time, you can spin up two instances and execute knowing that you will have no data races possible. Does that make sense? So to summarize, parallelism, as long as there's no conflict on the accounts, as two VM instances running simultaneously. However, inside a VM instance, no parallelism. Nice. Cool. So going back over to, yeah, okay, we gotta dig into the actual details here. So I hope this is going to be compelling. Apparently, people liked it last time, but I'm a critic of my own work. But let's have a think. We're going to read a bit of source code from the Agave validator. We're going to look at, and I think this just helps build intuition for what's going on. But what is actually happening to receive a transaction? So we're going to need to process a message and set up this VM. And I don't expect that as I go over it, this is just going to click for everyone, but maybe it's going to dispel a bit of the mystery, because those components that I've shown, we're going to see a little bit of like, where do they get set up? So we'll start by processing the message. I'm going to bring that over here. We'll start by processing the message. So I'm aware that this is without context. This is just the point that we're jumping in. But inside the Agave validator, there is an SVM crate. And in here, there's something that processes messages. So remember, messages are the thing that a transaction signs a message, right? So a transaction is a signature and a message, and the signature is the signed message. So the message component has the instructions of what we actually want to process. So when we process a message, this method calls each instructions in the message over a set of loaded accounts. So in here, what I want to draw attention to, there's always I encourage everyone to try and go through and read the code that's in here, because things like this, they feel really, really overwhelming. But then you start to notice, you're like, oh, a bunch of this is just related to measuring compute units, and this is just setting up the initial context. And then it just sort of starts to fall away, where you see, oh, okay, so we're just doing a for loop for every program ID and instruction inside a message. And all of that's just setting up timing information and making sure that we have enough compute units. But eventually, what we're going to do is we need to create this result. And where did that come from? It's funny because I just said it's it's so easy. And then now I can't see it. Am I crazy? Zip, enumerate, invoke, prepare, next top level instruction, math error, compute unit 0. Oh, here we go. So sorry, that part that I selected actually was more than that. Instead, how we get the result of the processing the instruction is we need to go to the invoke context and we need to process the instruction. So this is different than if we had a precompile. So a precompile being as if there was there are some programs which maybe this will be a good opportunity because I don't know if I'm going to get a better opportunity later with time. But sometimes there might be things that we need access to or that we don't want to compute inside this sandbox because it's too expensive. It's not really a threat to go from the outside, or it's things that are just we need to know about the outside world to do it. Like if we're going to get a block number or a timestamp, or if we need to do logging IO. So those things can't be processed as SBPF bytecode. And so what we have with these VMs is the ability to do syscalls. And a syscall is a routine that says, okay, don't process something more here inside this VM. Instead, hook via an API that makes sure this is valid and verified, but make sure that I'm going to call a function that is defined out here, like in the text segment, and it's going to process something for me, and then it's going to provide me with the result of that inside my VM. So it's a syscall to the outside world. And a precompile is when we have a deterministic process that we want to do in that outside world. So examples of this are like cryptography. If we want to do, SECP like KR1, I don't even know. You know what I mean? You could the famous cryptography things. You don't want to be processing SBPF instructions to be able to do that. You just want to call to the outside thing and know that this isn't really a threat. You're just doing a hash of this thing essentially, right? So you access those precompiles, but otherwise, what we want to do is we want to process an instruction. Now, depending on what that is, as we go over, processing that instruction, it's going to need to. So it's not very exciting at this level, I guess. I probably could have skipped a step, but the first thing that we need to do is we need to process this executable chain. So let's go to that because that's the more exciting thing. And this is where we're going to decide what are we going to call. So remember that if we want to call a user-defined program, we don't just give it the address of the user-defined program. Instead, we have to go through the BPF loader. But there's other built-in programs that we might need to go through, right? So there's, a whole host of things that we might want to be able to do. But the BPF loader is the thing that we invoke at least in relation to this talk to both store the transaction, store the program, and to invoke the program. So here, what we do is we say, okay, we want BPF loader, whichever one. And then coming down here, something that might trip people up is after we've set up all the logging, we then create this eBPF VM, this new eBPF VM. And you might look at that and think, aha, this is where I'm invoking my user-defined program, right? Because I'm creating the eBPF VM. Actually, this is what's going to invoke the BPF loader program, right? So it's going to invoke the eBPF loader program. And if that program, so by the VM invoke function here, and if the instruction that you're providing it is a execute instruction, it'll then create another VM to run your bytecode, the bytecode that you wish to execute. So let's see. I just showed the okay. Let's go into this invoke function. Oh, that's what I was just showing. What about this entry point? So now we're in the Agave program's BPF loader section. And so here, what I'm showing is this is the declared entry point here. And what we need to do is process instruction inner. And this is where I'm saying the instruction, depending on what you provide it. But if you want to perform a execute, let's see. So match. So So here is where we have the call to execute. So we had to get an executable. Where did we get that executable from? Oh, so right there. So okay. So from the program cache, you can load out the executable, and then you want to be able to execute it. And so this is part of the BPF loader, right? Like depending on what program you got, but this is how you would execute your own program. So let's have a look at that execute. What's going on there? Um, this execute one. So if you guys weren't compelled by watching me just scroll over GitHub Rust code, this is where I'm going to lose the rest of you, because this function is massive. It is an absolute beast. But there is this executable here provided, and so remember that's the bytecode function that we've read in from our BPF loader, and obviously there needs to be some context to invoke it under. That it's always in an environment, right? But this program, I mean, is really like it's huge, right? Like it's you're like going through it like, okay, and that happens next, and that happens next, and that happens next. But let's see if we can pull out some information that's going to be important for later. One thing that is important for later that I'll highlight now, even though I haven't explained it, is at this point that we've decided that we're going to do execution, we want to be able to create a Boolean called use JIT. And so that's depending on the architecture, right? We need to know that the validator is running x86 in order to use JIT. But we check the executable that we provided as an argument, and we see, okay, it doesn't have a compiled program, in which case we can use JIT. Some other things that are important to notice as we go here. So this is all talking about serialization. So this here regions, which is so here we should see like this is let. We're assigning to this tuple of information here. One of the things that we're assigning is regions, and that is a serialization of parameters like the instruction context and information here. That serialization is going to account for. And remember, I can always make mistakes, but if I understand things correctly, that serialization should account for input data here. Um, and and then what we will see is those regions are going to get provided account region addresses. So here, where save the account addresses. So okay, no, create VM time. Here, this is where we call the create VM macro, and so we provide a VM here, I guess. I don't know where that came from. Where did that come from? Or it is a macro, so that might be um yeah, let mute VM. Okay, there's some magic going on there. But let's go in and have a look at what's in that macro. But for now, we know we provide it with VM, the executable, the actual program that we want, region. So far, this just has the like we can think of the input data and that stuff, the account metadata, and the context that we want to have this VM run under. And once we've created the VM, we can think that this VM here that must be the output of what's going on here. We end up getting the VM stack and heap. So we can see some familiar names of what we're with. We're going to go have a look at things a bit deeper in a second. But what I want to get to is at some point, we're going to call, if we have a result, that must mean that we called an execution. So we sometimes scroll past things. Drop VM. Where did we actually execute? What I should do is I should go, I'm sure it will be in invoke. Invoke context. Maybe it's just too big. Okay, I can't see it, but somewhere in there where I'm scared I'm going to run out of time, but somewhere in there we're going to actually invoke the executable. Now, let's go back out. Oh, vm.execute program. That's what I want. Where was it? Oh, I was right by there. I was right. Yeah, okay. So it wasn't invoke, it was execute program. So we've created our VM by this macro that I haven't shown you yet. And this is created we provide it now. We say execute the program, we give it the executable, and whether or not it should use JIT compilation. In reality, it uses SBPF, but you're going to see eBPF a lot everywhere, Armstrong. So that's where we start executing things. And now we can think, okay, cool. So we're moving off from the SBPF world, and we're now going to go into we're moving from the validator world, and we're saying, okay, let's execute the logic with the SBPF VM. So that's where we're doing this. We've just done all of the setup and we have this VM, and we provided the execute with an executable and whether or not it should do JIT compilation. Cool. So the next step is we can kind of shift our perspective, right? And so as we do it, we should note that I copy pasted this slide. And so this says validator perspective, but it should say SBPF perspective. Not bad that I've only found one typo so far, though. But let's think of what's going on from the SBPF perspective. We have our struct executable that I showed you before. So look now, we're not in Agave anymore. We're over in SBPF, that repo that I showed you before. In the L file, this is our executable. So we've already seen this. Remember, we have our text section, we have our read-only data section. Okay, cool, nice. So that was provided as an argument to VM execute. But something that that I want to talk about is if we're going to execute a program, what we need to do is we need to verify that program. So we will have, as part of the execution steps, verifying the executable. So what does that mean? What does it mean to verify the executable? Well, I showed before the instruction set architecture here, but what I didn't show was down the bottom afterwards, we get a specification for some things that must be true here. So verification. These are some things that must be true of an SBPF program in order for it to be well formed. So for every single version here, and then we see down for V1, from V1 until V1 until V2, V3, yada yada. But things like the bytecode length must be evenly divisible by the instruction slot size. The bytecode must contain at least one instruction. You can't have an empty program. All sorts of things like this. The offset of the jump instructions must not point to the second slot of a load word instruction. There's just a bunch of things that are considered well formed, but we need some way of actually enforcing it. And that's where that verify function is. But what is the verifier that will actually do this? So as part of the SBPF verify thing, it provides a thing called a requisite verifier, the mandatory verifier for Solana programs to run on chain. And all it needs to do is implement this verify function, which admittedly is a really, really big one, but it's not so big that it's not understandable. All you have to do is see, okay, let's break it down. What goes on? We got a bit of like setup thing, making sure some stuff to do with bound. And then we have this massive while loop that is the entire thing, essentially. And what is it doing with that while loop? Well, it's going through the instructions. It might not be so obvious, but it's going through the instructions and it's calling all of these verification functions on those instructions. And so it has these like massive match statements or switch statements, maybe is something people are more familiar with, although given that we're at a Solana thing, a match statement. But it does like make sure that the, all of those things that are in the, what did I say? The ISA back there, they end up getting called in the instructions to make sure they're well formed. And so what we see is up above in this file, this is where all of those functions enforcing those invariants are actually defined. So you can go through and see what all of those things mean in here. Check the program length, check that the immediate is non-zero, check the Indianness. Things must be aligned, all that sort of stuff. The offsets have to be correct. So all of that, assuming that you go through the entire program and it verifies correctly, so you're happy enough, then you go, sweet, we have a well-formed program. So now what we can do is go to the VM initialization. We know our program is well-formed. Let's initialize a VM. So I guess I did kind of skip a step. So did I end up, I should have, I didn't provide a link, so now I'm gonna do it the old-fashioned way. No. Yeah, agave. So I'm just gonna try and find this. I can show you guys here. So I'm gonna try and do this locally. So let's look for macro rule. So it must have been a macro because I saw the create VM macro rules. Create VM. Sweet. It's in this file at this point. So this is the agave validator, and there's a lot of stuff that you could get lost in here. So I just wanted to grep for the thing I didn't know, couldn't remember where it was, but I knew what I was looking for. But remember, I talked about this create VM macro, which is creating the SVPF virtual machine. And so this is in program runtime source VM. Let me know if you need me to zoom in or anything. But inside here, what gets called is, let's go through the macro, because what it does is it ends up, it calls this create VM function. So this is the create VM macro. Now, if we go create VM, not time, there we go, create VM here. So this is taking an executable. It's also taking some regions, vec memory region. We haven't really delved into that yet. And it takes a slice to some U8s, a mutable slice to some U8s, and that's what it's provided as its stack and heap. Very, very interesting, right? We're starting to color and figure out, where do these sections come from? We've already seen where this came from. We know where this bytecode segment came from. It came from the executable, right? And so did the read-only data. And now we're seeing that we didn't see where those slices came from, but we can see that there's a heap and stack, some slices to some memory somewhere. Very interesting. And so this is calling our eBPF new. That's what it's calling to create the I can do it, the virtual machine. Okay, cool. So that's the VM initialization. Now we've seen that that's what gets called on the agave side. So let's have a look at the SVPF side at what it actually is. We're back in the SVPF world now, and we're looking in the VM here. So the VM being this struct that I showed before, and it has all of the things necessary to do the bookkeeping. I showed like the registers. It has a memory mapping, and we can provide to it. Remember, the executable and execute it. Now, when we create the new VM, there is the version and this memory mapping. And so that memory mapping, that was where we had this stack and heap here, and they get provided to this memory mapping along with the program. That's the executable, right? And I think the rest of this is some stuff to do with the other data segments. Now, cool. That's how we create the VM. What's the next thing that we want to do? We want to execute our program. That's what we saw. So what does that look like on this side? We're back in SBPF VM and we want to execute the program. We got to give it, it's a method. We need to have a VM to run it on. Whether or not, the executable, and then whether or not it's interpreted. So it will be going back here at this point. This is back inside the Agave BPF loader. This is matching up to that VM execute program executable, and then this is the interpreted thing. So whether or not to use JIT. So what happens in here is we end up getting the payload out of the oh sorry, maybe that's already happened, but either way, we get our instructions. We want to take our instructions, and what we do is we have this if else statement here, right? So at the start here of the if interpreted. So if we're using the interpreter, then what we do is while the interpreter can, it's going to do this step, and that step is the thing that is processing the functions. The other option is that we are not interpreting and we have a JIT program, and so that's where we have a compiled program that is able to be run natively on our machine. So that's like a crazy thing for me to just like gloss over, is the difference between these two things. But there are two ways to run the instructions for this SBPF. You have an interpreter and you have a JIT, a just-in-time compiler. So the interpreter here is going to be this this program. So there is the VM and the executable here, and how it works is like those instructions that I showed you in the ISA. To execute them, we're going to find a massive, so this is inside step to step through the executable. We're going to see that there's a massive match statement, which is every single one of those. It says eBPF, but think SBPF. SBPF opcodes. And what it's going to do is decide, it's going to actually do the processing for each one. So whether that's moving the stuff inside the registers or dealing with memory, allocating to the heap, like all these sort of things. This is where all of the logic of the actual program gets processed. That is different than what happens in the JIT case, which is the one that I opened over here. Instead, in the JIT case, what's happened up front is the JIT program is storing as its text section the x86 machine code. So that is storing instead when it comes new. That is storing instead, or maybe it's not. Sorry, maybe I'm getting things a little bit confused. Maybe it has to do the conversion up front, but the idea is that this is not SBPF code. This is x86 machine code to run natively on the microprocessor of the validator. And so what it needs to do here is, where do we see it? I'm going to find it shortly. JIT compiler new. Compile. Exactly. This is what I was wanting. It compiles a given executable. So you want to provide it with a self, and it's going to give you back a JIT program. So that's the x86 program, right? And what we'll see here is another massive match statement. And what this is doing is instead, let's go down to somewhere where I feel like let's look at add. Add is an easy thing. Adding 32 byte register with an immediate. Now, if we match the instruction as that, what we want to do then is figure out how to convert it into an x86 instruction. So this is arithmetic logic unit. How and it's talking here, it's got to do like sign extension and stuff like that. But there is a way of understanding what this means in SBPF, converting it to the x86 world. So that's what happens up front, and then these are run immediately on your actual processor of your validator. So with that in mind, those are the two. Wait up, I want to do that again. Oh, so that's what I show here. There's SBP, the interpreter, new and step, and then there's compile and invoke. I guess I didn't show invoke, but going back over to here. So once you, I was skipping ahead. Once you have the program, you can actually invoke it, which is just running the x86 program. I think we would even be able to see macro rule statement expression ASM. Oh yeah, so this is going to be necessary setup to start the program, and then we should see it sets the stack pointer. Maybe not as easy as I thought to understand, but this is invoking the program that way. So I'm aware that I'm a little bit over time. I am going to take license with what you said, Mike. I just want to talk about one final thing, which I think I've tried to fill out a bunch of the puzzle and how things connect, but I think there's still one thing that might not be very satisfying in people's mind. And what I want to show is this idea of the memory mapping. How do things connect in a way between what the validator has and what I showed as that SBPF world? Because we sort of saw, oh man, come on. We sort of saw, okay, we saw where the serialization of some things are. We understand that this comes in as loaded from the program. And then we saw that there was slices here. The slices are references, right? So where are they references to? Where does that even come from? So let's solve that mystery. Let's start to understand that. And maybe the other thing that I'll point out is where are those numbers that I mentioned here? Where are they even defined? Where did that come from? Well, where that came from, I'm just going to make my life easy again. I'm just going to close all these. Where that came from is inside the source here. The VM is going to be defined by this eBPF thing here. And what we'll see here is this is where we get the definition of those memory addresses. So what I did last time and what I'm going to do again here is hope I can use my computer properly. So actually, let's do that. Let's do this. And cool. Now we can see both. So I'll even zoom in a little bit more. I want that to be more visible. Is that legible? I hope so. So what I want to show here is where did this address space come from? Well, it's defined over here in this eBPF RS. So what we can see is virtual address bits is 32. So 32 bits of virtual address. A memory region size is 1 shifted left 32 bits. So you can think of that as 2 to the power of 32, right? So that's how much is one memory region, and that's ends up being what we see offset by here. The bytecode start is at 0. So that's this address here, 000. The read-only data is just memory region size, which was 1 shifted by 32, which was virtual bits address. So this is where the bytecode starts. Oh, sorry, that's where the read-only data starts. I saw that word and started reading it, but that starts at 0. It's 1 shifted by 32 that the memory region starts. The stack starts at the memory region multiplied by 2, so that's where we get the stack starting here. The heap is the memory region multiplied by 3, and the input data is the memory region multiplied by 4. And then given the size of the memory region, I've put a cap on here at 5, but by the time you get to there, you're outside of the address space. So that's where that stuff came from. Just wanted to, I thought that might have been a little bit more satisfying to see where that came from. But let's talk about what's going on, because we saw this before, this memory mapping, right? What we saw in particular was when we were doing this create VM, which when I went and I found where that actual function is, that's doing a create memory mapping. And if we follow that function, which if I restart the Rust analyzer, it's upset. Okay, well, you can't have it all. So create memory mapping. Sweet. There's only one of them. There we go. It wasn't that hard. So inside the program runtime, there's this vm.rs, and it is able to create a memory mapping. What it does is it takes the executable, the stack, the heap, slices, and from there, we should see the call of a... Oh, sorry, this is that vector. Yeah. So this is where it turns it into those memory regions. So this is the connection. So I got a little bit lost this time. That's that connection to the layout here, the memory regions, right? The executable, we want to get the read-only data section out of it. Yeah, okay. So now let me try to correct myself. Oh, and that was just on here, create VM, that whole time. So if we go to the top of this file, in here, we should see this thread local memory pool. And this has a VM memory pool new. Now, this is important. This memory pool, this is what gets used to create that stack and heap, right? So what's going on with that memory pool? This is happening inside this instruction here. So that stack and heap, those are the slices that got sent to the create VM here, which I go stack and heap, those slices. So that somehow came from this memory pool. So what's going on there? It's still going to be mean to me. So let's rip grep for struct VM memory pool. Inside program runtime mempool, what we'll see is a struct, the VM memory pool, that has these pools. Not very exciting. The pool is just defined up here. The actual exciting thing is both the stack and the heap are taking aligned memory. Okay, and when they do, when you create a new VM pool, this aligned memory gets 0 filled. So for the stack, it's the stack frame size multiplied by the maximum call depth. For the heap, it's however many bytes are available in the frame. So the question would be, what is this aligned memory? Sure, it gets 0 filled, but what is it? Like, we get back a slice, but where and what did we define to even get that slice? So the aligned memory comes from up the top here, Solana SVPF aligned memory module aligned memory. So this is that SBPF crate. that we were looking at back, back here, or maybe I can, where did I do it? Do I have one? Here we go. Back here. So SBPF. If we go into the source code here, into aligned memory, what we'll see is an aligned memory has a memory component, and that is just a vec of U8s. And so the U8s are bytes. So the aligned memory payload is just a vec. And we get a slice to that vec that comes out the other side. But what I want to show, so zero filled. Okay. It might not be clear yet. So what this is doing, but a vec is always allocating its memory on the heap. So if we just go to the standard lib rust vec in standard, I want to go to the source code. So a vector is a struct, right? And importantly, it has an allocator. And so this allocator, that is what is responsible for allocating onto the heap. And so that gets achieved through this raw vec here. But if you want to have a good pictorial mental model of what a vec is a pointer, length, and capacity that is stored probably on the stack. If you say like let x equal vec is type vec. But importantly, the payload of a vector is always on the heap. That is the point. It gets allocated onto the heap. So the point of what I'm saying here, I need to bring it all back. But what I'm trying to say is the important connection is when we saw with the BPF loader, this memory mapping getting created, and there was a slice to the stack and heap, a vec was originally created. So these are slices to heap memory of the validator. So in this picture, what we can think of is we've now figured out the heap and the stack here. These are the regions that the bytecode program is processing, and when it's allocating to them, that all of that is just done in slices to heap memory from the validator. So that's like the connection back. I think I'm gonna have to call it there. I think I got through everything I wanted. Yes, so yeah, I mean, there's tons more to say, but I think that's all I can do for 2 hours.
All right, thank you very much, Daniel, for your time. It's
Yeah.
like 2 hour. It's actually extended to 1 hour, and actually there are also some chat, also some questions. If you can
Yeah, please.
take that questions, that'd be great. You can take a look of the in the chat.
Yeah.
It's a wonderful chat. So this one will be recording, and
Mhm.
so all the videos will be listed in on the largest for developer platform, which is
Mhm.
HiveQuest Open Build, and also I don't know if Blueshift has listing the video, but I think in the future they will. Also like Upstream DAO and HiveQuest.
Sure. Yeah, well, I must say I hope I haven't made any mistakes because I wasn't involved in writing any of this. I just read code. So hopefully I understood it correct.
Wow, it's great enough actually. Yeah, I'll take it to you like to see the chat.
Mm. I see a question in here. So, if we have unaligned memory access, does the verifier reject them or will they get through the runtime? So, uh, we have at the moment aligned memory as the data structure there, and this is showing that everything is completely aligned. Um, I guess what I want to say is there's kind of two ways that I could interpret your question. The first one is, were we using aligned memory here? And as in, could we do an unaligned read with that? This is like aligning that when there is the memory in this process, does it need to be aligned to the same representation here? At the moment, it does. However, I think in the future you will be able to have different alignment between the two that will be relaxed. But another way that I could interpret your question is within a type, we can consider that types always have an alignment, right? There is a layout for any type. And generally speaking, we only consider aligned reads, as in if you have 8 bytes that is your type, then you point your pointer to the start and you read for those 8 bytes. You don't offset your pointer by 1 and try and read because you don't know what you're going to read. Now, you can do unaligned reads in Rust. I believe they should be undefined behavior because you're not conforming to the type system. But that ought to, I'm going to say that I believe that that is rejected by the runtime here. But I want to ask a question back to you, even, because my intuition is always that you won't be able to do something like that. But for undefined behavior like that, do you think that the Solana runtime will prevent it or that it would allow it? And I guess this is open to everyone in the chat. Does the Solana runtime, if we try to do things like with unsafe Rust, unaligned reads, have pointers to places in memory that aren't initialized, things like this, does Solana reject these programs or does it allow them to exist? I guess I'll make it a rhetorical question because the thing is, more things than you would expect are actually permissible, and you can create programs that exhibit undefined behavior like this. Yeah, I hope so too. Maybe one time I should do another session and we should make it a practical one and we should try and find out, because that sounds like a lot of fun to go. But you'd be surprised. You are given a lot of license to hurt yourself, like what you say there. You say it prevents us from hurting ourselves. It's there's more leeway than what intuition you would think. I see a bunch of questions in here, but I feel like I did address most of them. In reality, does Solana use SBPF or eBPF? It uses SBPF, but often you're going to see nomenclature for eBPF. I mentioned that with the VM processes, whether they're in parallel or not, that the one of these is sequential, but that you could have two of them running concurrently, as long as the locks did not conflict. And I mentioned about the stack here is not conforming to the same rules as this stack growing down because this is a different virtual memory layout. And then, yes, I will share the slides. And I don't know if there's any other questions. Is there another place that people are asking questions, Mike, or is that all of them?
Yeah, I think it's all of them. Usually we don't like how like people raise hands and answer questions in
Yeah,
Mac.
cool.
Yeah, but thank you very much, Daniel, again, and for being here and give such a wonderful presentation. And I can see you actually prepare a lot for even for this, like even for today's one. Thank you very much again for your time, and it's really wonderful presentation. And I believe that it's will significantly helped Chinese developer community who are interested in security and also the execution level, especially for BPF, because to be honest, this is the first time I think there is an instructor talk about like this topic in the
Mm.
Chinese developer community. So actually, you give a very good beginning for us to hopefully you can explore more. We can encourage more people to explore the open source and also the execution level. All
Okay.
right.
Yeah. Well, wonderful. Well, I thank you for allowing me to be here, and I want to encourage everyone that if you had more questions on this, like I don't feel like I'm the expert, but I promise you I'm very friendly. If you reach out to me with questions, I'll earnestly try to answer them. So hopefully, I've inspired some people to go and investigate.
Great. And please also like follow Daniel's Twitter. Like actually if you follow the Solar's Twitter, he actually listed here. Let me find this Daniel's Twitter in the chat and let us follow you.
Okay,
Ah, Daniel.
sure. I'm
Yeah.
not very active on there, but I'll try. I'll try to make sure. So if you send me a question there, I'll try to.
Yeah,
Uh,
or GitHub. Which way you
yeah,
prefer?
yeah, yeah. That's true. I
Let
do
me
have a
see.
GitHub. You can find
Okay.
me. So I think Mike will have my um
Yeah.
my GitHub is just DK Cumming, and I think my Twitter is Daniel K Cumming. Um,
Yeah.
if
Let
you
me.
want to know my socials,
Okay, thank
and
you. Thank you for.
I
Hmm?
encourage everyone to apply for Rectoff if you're interested in things like this. This is the kind of stuff that we go through.
Great. There's another the students actually macro one. So who is the guy actually like listen to your speech and recommend suggest us to to have you. So he's still there. He's still with us in the
Yeah,
chat, but he speak in Chinese in the chat. But I do the translate.
nice.
Okay.
Well, awesome.
Okay.
Good to see you, and thank you.
Thank you, thank you. All right, let's keep in discuss in a group and in GitHub. All right.
Yeah,
Thank you very much for
wonderful.
your time. And
No, thank
all
you.
right, that's all for it. Thank you. See you.
Okay, thank you, everyone. Thank you for your patience and attention. I'll see you next time.
See you. Bye.